Welcome back to the data engineering track of Spark Summit Amsterdam, and thank you for coming for our talk. We are coming from the Databricks Amsterdam office, which is just across the street from here, as you've probably heard already today. And we are both software engineers on the BI experience team there, which is working on generally improving the experience and performance of business intelligence and SQL analytics workloads using Databricks. So what we work on is integrations with tools like Tableau, integrations with tools like Power BI, Databricks, ODBC, JDBC connectivity, but also we work on core performance improvements to Apache Spark that help SQL data analytics workloads. And today we'd like to talk about one such improvement that's going to be released with Apache Spark 3.0 early next year, and which helps prune the data to more efficiently skip partitions when reading data from partition table. And I will give the floor to Bogdan, who actually implemented this optimization, to describe what it's doing.
Awesome. So before presenting and explaining how dynamic partition pruning actually works, let's take a look at one of the performance results that we have seen with a TPCDS query on over a 10 terabyte data set. This plot shows that query 98 executes 100 times faster with dynamic partition pruning. This is really impressive. Some of you may wonder, how is this possible? But the answer is actually quite simple. Read only as little data as you only need. In standard databases, pruning means that the optimizer will avoid reading files that cannot contain the data that you're looking for. So for example, in this simple query, in which we are trying to match and identify records in the sales table that are from Monday, from a specific day, this translates into in a simple form, translates into a filter on top of a scan. Most query optimizers are pushing down the filter from the top of the scan down as close as possible to the data source in order to be able to avoid scan the full data set. However, this partition pruning is the technique itself. It's most effective, and it works at its best when both the filter is pushed directly into the scan, and also the data set is partitioned. Because in that case, if your query has a filter that is on partition columns, you can actually be able to skip complete sets of partition files. However, in reality, data engineers don't just execute a single query, a single filter in their queries. And the common case is that they actually have dimensional tables, small tables, that they need to join with a larger fact table. So in this case, we can no longer apply static partition pruning because the filter is on one side of the join, and the table that is more appealing and more attractive to prune is on the other side of the join. So we have a problem now. Data engineers that are designing their ETL pipelines, what they do is that they are joining the dimension tables with the fact table beforehand. And in this way, they put themselves into a position in which they can still trigger static pruning over a single table. And then they execute their queries, their filters in separate queries. So this is actually illustrated in the following diagram. There are obvious downsides to this approach, because first you have to execute this quite expensive join. You are duplicating the data because you have to generate another intermediate table. And this table can actually be quite wide, right? Because you take a bunch of smaller tables that you are joining together with a large table. And not only it's wide, but it's actually extremely difficult to manage in the face of updating the dimensional tables. So whenever you're making a change, you actually have to re-trigger this whole pipeline all over again. So what we can do. In this talk, we are going to talk about a radically different approach in which we are going to do filtering using dynamic pruning. The basic goal of this optimization is to be able to take the filtering results from the dimension table and use them directly to limit the data that gets to be read from the fact table, exactly as in this diagram. So let's continue with a high-level description of how Spark SQL works in a nutshell. Users typically submit their queries from their favorite API, their favorite programming language, right? So we have data frames, data sets, we have either SQL. And Spark takes this query and translates it into a digestible form, which we will call the logical plan of the query. During this phase, Spark optimizes the logical plan by applying a set of transformations, which are rule-based transformations, such as column pruning, constant folding, filter pushdown, the ones that I already mentioned. And only later on, it will get to the actual physical planning of the query. During this phase, Spark generates an executable plan, which will be used to distribute the computation across clusters of many machines, just like I'm showing here. OK, so in this talk, what I'm going to try to do is to explain how dynamic partition pruning can be implemented at the level of logical planning with a simple approach, and then how we can further optimize it during physical planning. Let's start with the optimization opportunities that we have at the level of logical planning. So we will consider a data set that is partitioned across multiple files. And each partition will be differentiated by a particular color. On the opposite side, we will have a smaller table, a dimension table that is not necessarily partitioned. And then we have the typical scan operators on top of these data sets. Whenever we are filtering the dimension table, we will consider an example in which only rows that correspond to two partitions on the opposite side of the join are actually relevant. So when we will complete the final join operation, only those two partitions will actually be retained by the join, right? So this highlights that there is we don't need to actually scan the full fact table because we're only interested in two filtering partitions that result from the dimension table. What can we do about it in order to avoid this scanning? So a simple approach is to basically take the filter from the dimension table, incorporate it into a subquery, and run that subquery inject it below the scan on the fact table. And in this way, we can figure out that when we are planning the fact side of the join, we are able to figure out which data is actually needed for this join. This is a simple approach, but however, it can actually be expensive if we don't have a good way, if we don't have like a good heuristics to assess the selectivity of this filter. So what we want to do is to actually get rid of this subquery duplication and figure out a way to do it more efficiently. And in order to do that, we're going to take a look at how Spark executes a join during the physical planning, how Spark transforms the query during this physical planning stage. If the dimension table is small, then it's very likely that Spark will execute the join as a broadcast hash join. Whenever we have two tables that are hash joined, there are a number of things that are happening. So first, Spark builds a hash table out of the dimension table, and it's actually called the build relation. After it executes this build relation, it will plug in the results of that side into a broadcast variable that Spark will distribute across all the workers that are involved in the computation. By doing so, we are able to execute the join without requiring a shuffle. So what happens next is that Spark will start probing that hash table with rows that come from the fact table on each worker node. Now, there is clearly a natural barrier between the two stages, right? So first, we are computing the broadcast side of the join. We are distributing it, and only later on we start probing and execute the actual join. This is quite interesting, and we want to be able to leverage this into our optimization. Because this is quite exactly what we have mimicked with, at the level of logical planning with the subquery. So here's what we are actually going to do. We are intercepting the results of the build side, so the broadcast results, and we are going to take them directly and plug them in as a dynamic filter on top of the fact side, inside the scan on the fact table. So this is actually a very effective and optimized version of our dynamic partition pruning, which Julek will continue to demonstrate through a set of experiments that we have performed on a real cluster with realistic setups and workloads.
Okay, so to evaluate this approach, we've tested it on the TPCDS benchmark, so Transaction Performance Council Data Science benchmark on scale factors from 1 to 10 terabytes, so with 1 to 10 terabytes of data, and running a master build of Apache Spark 3.0 on a 10-node AWS cluster composed of 10 i3 X-large machine instances. So that means it was a 40 CPU cores cluster in AWS. And we've run a current build of Apache Spark with this feature enabled. That is still like a development build, not a released build. And this single optimization to filter partitions dynamically based on propagating the dimensional filters improves more than half of the TPCDS queries by more than a factor of 2. And for several top queries, it shows an up to 18x performance improvement on the 1 terabyte data set. So when we look at the top queries that improved, and this is query 25, query 17, 15, 42, 6, and so on, we can see that top 10 of all TPCDS queries improve by factors that are like 10x. So like Bogdan mentioned, this improvement is possible because this partition pruning lets us skip scanning a lot of data. And in case of those top queries, it's close to 90% of the data that cannot be scanned because we propagate the dimensional filter directly into the scan of the fact table. And when we go to scale factor 10 terabyte, so 10 times more data, the speed up gets even more pronounced. And now with several queries, we are getting speed ups that get close to 100x. So this is possible to be super linear like that, because when you reduce the number of data processed, it doesn't only scale linearly, it can also help you avoid various performance cliffs that can make your query spill to disk or have to switch from like a hash-based processing to a sort-based processing. And by reducing the number of data by an order of magnitude, you often avoid a lot of those performance cliffs in query processing. So the query that speeds up the most in scale factor 10 terabyte is query 98. And we can see in this query that it joins a sales fact table with item and date dimensions. And the fact table is partitioned by date, which is like the most natural partitioning because data is often ingested also by date, and the cardinality of date that you keep in your database is kept at a reasonable level. And this particular query selects only 1 month of data from this dimension. And the sales table covers 5 years of data in total. So this is a 1 in 60th selection from the fact table. So close to 98% of the data can be skipped. So this could explain a 60x improvement in performance, but the actual performance improvement is close to 100x, close to thanks to the superlinear properties that I mentioned. So that query in Apache Spark without this optimization took over 20 minutes to execute on this scale factor and at this cluster. Now it can execute in a bit over 10 seconds, thanks to the highly selective filter that now can be pushed from the data dimension directly in the fact table scan. So to summarize, in Apache Spark 3.0, we implemented a new optimization called dynamic partition pruning that works both at the logical planning level to find the dimensional filter and propagate it across the join to the other side of the scan, and then at physical level to wire it together in a way that this filter gets executed only once on the dimension side, and then the results of the filter gets reused directly in the scan of the fact table. And with this twofold approach, we achieve significant speedups in many TPCDS queries, which represent typical decision support data science workloads. And with this optimization, Spark may now work better with star schema queries that join dimensions, and it may help you avoid ETLing data into white tables that are denormalized with all the dimension data put together into the fact, which makes the ETL process easier, and you can directly run queries on highly dimensional data, just like in data warehouses. Thank you for the talk. Thank you for listening.
So time for QA.
Hi, I'm Lior from Taboola. You've mentioned the dynamic filter. Is this like a new concept that is in the API or something internal? And another question is, suppose you have aggregate prior to the join with the dimension, and like what you've presented is mostly effective for predicate push down to the underlying data engine, like data storage like Parquet, but not all the time the data is organized in a manner that predicate push down could be utilized. Like I might be filtering by data that is spread among many blocks, and eventually I have to read entire blocks into Spark and then apply the filter after the scan. Mm-hmm. Okay, so the question is this something that can also be benefited from, even if predicate pushdown isn't applicable?
Thank you for good questions. So this is a form of predicate pushdown, and it is based on partitioning. So it is regardless of whether the actual data is in Parquet or in other format, but the data needs to be partitioned, and the partitioning must be stored in the meta store. So and then the join with the dimension must be on the partitioning key. So basically, the data must be partitioned by the key of your dimension, but often there is one such natural dimension that is naturally and often filtered on, and that has a cardinality that lets you manage this amount of partitions in the metastore. And your first question, I believe, was about whether it must be some special kind of filter. It doesn't require any special syntax. It may be any filter on your dimensional data. So for example, if you have a sales table joined with a date dimension and joined on a partition key of the sales table, so the sales table is partitioned by the join key, then it can be any filter or any of the columns of the dimension table, and it will get propagated directly to that to a filter on the partitions of the sales table. Okay.
I got my answer.
Question regarding what if I don't have an obvious dimension table and I have a filter which causing one of the tables that I'm joining to become, due to the reduction of data, so a dimension table. So I don't have any, so because for example, cost-based optimization try to do it by some analysis, so to have some statistics of the data itself. So how does it work in this case?
So if I understand your question correctly, it's like what happens if there are not this specific, if there's no specific case of a broadcast hash join, like if we don't have a small dimension table that will plan the join as a broadcast hash join. Well, clearly this, as I stressed out during the presentation, there are particular scenarios in which optimization will not be triggered. And the problem with that is the risk of having a not selective filter enough on the right side of the join. So this optimization will actually trigger only when your join is planned as a broadcast hash join. So we rely on stats that tell us that right side, one side of the join is below 10 megabytes. I think that's the default threshold in Spark. And at that time, we already know that will be planned as a broadcast hash join, and we can plug in this dynamic filter.
And did you try also to combine it with the cost-based optimizer that kind of can choose to?
So it's kind of implicit, right? Because we are interested in having small result sets on the dimension side of the table that gets broadcasted. Because that's the situation, the ideal situation in which you can benefit most on the fact table from that filtering. When you have like just a bunch of partitions that are of interest, and then you can skip a lot. So there are definitely rooms for improvement and looking into relaxing a bit more this constraint setting. But in that case, as I highlighted at the logical plan, you really need to count on very accurate statistics. So because you don't want to enter a situation in which the filter is not selective, and then you are duplicating a lot of work. So you're slowing down basically 2x your query.
Thank you.
Sure.
Hello, thanks for the talk. What is the max size of this dimension table until this dynamic partitioning is effective, and why?
So it is more limited by the partitioning than by the size of the dimension table, because the fact table has to be partitioned by the dimension key. And if the partitioning is done and maintained by the Hive metastore, then the practical limit for the number of partitions is probably in the tens of thousands. So if you have like a dimension table of tens of thousands of rows, and then you want to like filter on the features of those dimensions, then That's probably roughly the limit.
Yeah, and another point to mention here is that the way it's implemented right now, it will work out of the box. So you don't have to do any sort of tuning, any additional parameterization. Whenever you have a broadcast hash join, then this optimization will trigger, assuming that you do have partition data and a filter on the dimension table. So hopefully that will improve a lot your ETL pipelines.
One more question over here. That was extremely good presentation, by the way. Why it can't be implemented for the other joins? Why it's just for the broadcast joins?
You mean why the filtering?
Yeah, why does this data pruning appears only for the broadcast joins?
If it is not a broadcast join, this first approach at the logical planning level will still trigger. But if you have a sort merge join, then two sides of the join are executed at the same time. So you cannot prune the fact side based on the results of the build side, because the build side of the join is not yet finished running when the probe side is already scanning. So the first part of this optimization with SubQuery duplication will still work for other sides of the join, other types of the join, but it is a bit more unsafe because it duplicates that subquery, and if that subquery turns out to be expensive, it may do more duplicated work on that subquery. So there are some heuristics in place to look at, like if that subquery that it copies there are, because so it actually duplicates this scan dim table and filter dim on this logical plan. So if it is in fact a small dimension table, then probably just duplicating it and running it twice doesn't really matter. But the statistics available for Spark are imperfect, so it may turn out to be something complex and complicated, and it may be like a complicated subquery on your dimension that in itself is expensive. So it will still work like that for other types of joins, but when you have a broadcast hash join, it will make sure that it has no overhead of duplicating this work by reusing the result of the broadcast for the filter. And that's thanks to the characteristics of a hash join, that in a hash join you have to first be done with the build side before you start working on the probe side, while a sort merge join processes both sides at once.
Is it worth to say you do the pruning just to get the data, or size of the data less than 10 meg, so that you can broadcast the joins?
So I think it's the other way around. So first we are broadcasting and then we are pruning on the other side. And what Juliusz just said is basically this barrier that is characteristic and specific to the broadcast hash join between generating the build side and broadcasting it, and actually starting and computing the join by probing that hash table that gets on all nodes. Cool. And this is like in sharp contrast with the sort merge join. And yeah, so we are waiting basically to build this broadcast variable, and then we can take those values. Basically, it's a list of keys that we can take and build this customized dynamic filter that we are plugging in directly into the scan on the fact table.
Thank you.
Yeah. One more.
Hi. Well, thanks for the great talk. I just have a more, I'm already thinking of how I'm going to apply this. I have a specific step where I actually join on 4 keys with the fact table. So will I have to partition the fact table by the 4 keys, or do I just pick one based on cardinality, or how would you recommend I get the best out of it in this situation?
I think it will work with a join on just one of those keys based on cardinality.
Okay, thank you.
Yeah. One more question there? Or,
yeah, actually, I have two, but small questions. The first one, is it works for equal join only, or it's possible to join non-equal? And another one question, if table partitioned by few fields, will it applicable in this case? For example, if I have in dimension only 2 fields, so will this dynamic partition pruning works? Thank you.
Could you clarify your example? So you have a dimension with 2 fields, and how is it joined with your fact table?
Yeah, for example, fact table is partitioned by year, month, day, and brand, for example, it's table of sales. And I join dimension, like calendar dimension with dates on to the sales table. So, and my join condition is only by date, but not by brand.
Yeah. So if your fact table is partitioned by date, and your filter is on the other column of the dimension table, then this will work. So it will take this filter on the other column of the dimension table and propagate it to the fact table based on this join of on the partition key. And as to your other questions about non-equijoins, no, it works only for equijoins.
One more question.
Thank you. Earlier in your presentation, you showed us that you try to replace this subselect filtering. My question would be, is it possible that if I have a table which are partitioned by multiple columns, which have different filter conditions, that the partition pruning, in that case the dynamic partition pruning, will cascade this filter down to the rest table? Means I have a year and I have a month, and it filtered first by the year. Does it filter automatically down also by the months?
So you mean that you have a dimension filter on a year, and then like month is like a different column of your dimension.
Exactly.
But the join between dimension and fact is on some artificial key of the date dimension, right?
Exactly.
Yes. So then it can be a filter on any column of the dimension table. Like it could be a year, month, day of the week, weekday, weekend day, whatever features you have in the date dimension. And it will be propagated over to the fact table based on the artificial join key the fact table is partitioned by.
Okay. Does it work also if it's part of the join condition?
What do you mean if it's a part of the join condition?
Let's say I have these 2 columns. I have one column where I said it's my year. It's part of my join condition, and I have also the months.
If it's part of the join condition, then I believe it should already work even without dynamic partition pruning, because if it's part of the join condition, like the optimizer can figure it out at static level, just looking at the plan, that if you join on a year and on the dimension you just select year 2019, then statically just looking at this query, without any runtime information, the optimizer can already figure out that the fact table should also be filtered only to year 2019. So that should work already without dynamic partition pruning.
Yes, but does it work also with a range?
Excuse me?
Does it work also if my join condition is in a range that I have not an equal sign, or really a hard condition? So there's a range where I try to join on?
No, so it works only for equijoins. So it's, yeah, that's a limitation at this point.
All right, no more questions. Thank you so much, Bogdan, Juliusz. Thanks everyone for attending the session.